In this video, we're going to learn about the national grid, which is the system through which electricity is transferred from power stations to consumers, like homes and businesses and factories and offices. There are a few different parts of the national grid, which are specially designed to ensure that not much energy is lost when that electricity is transferred through the cables. Please do these questions in your exercise book, pause the video while you do that, and press play once you're ready. You should have now done these 5 questions. Here are the answers. Pause the video to mark your work and press play once you're done. You should have now marked these questions. These are all important things to understand how the national grid works. I've also put in a question about changing units from megajoules into joules. You should also know what kilo means, what mega means, what giga means. All of those prefixes are important. So let's just quickly check that you know that. What does the prefix capital M mean? Say your answer to the video. You should have said that it means mega, which means that you have to times by 1,000,000 or times 10 to the power of 6. What does the prefix capital G mean? Say your answer to the video. You should have said that capital G means giga, or times 1,000,000,000 times 10 to the 9. What does the prefix K mean? Say your answer to the video. You should have said that the prefix K means kilo, which is times 1,000 times 10 to the power of 3. So here's a diagram of the national grid. Pause the video to take a look at it and press play once you're ready. So there are only 3 parts of this diagram that are actually considered the national grid. And that's everything inside this box here. So the step-up transformer, the transmission cables, and the step-down transformer are part of the national grid. The power station and the consumers are not considered part of the national grid because the power station is where the electricity is made and the consumer is where the electricity is used. The national grid is the part where the electricity is transferred from the power station to the consumer. So the simplest question you could be asked is, what are the parts of the national grid? What would you say to that question? Pause the video, say your answer, and press play once you're ready. Hopefully you've said that the parts of the national grid are the step-up transformer, the transmission cables, and the step-down transformer. We're now going to look at what these parts do. So the first thing we're going to do is focus on these transmission cables. So the transmission cables are where the electricity travels through to get the consumer. Now, you'll remember from previous study of electricity that when electricity passes through cables, when current passes through cables, now these cables are bundles of wires, so big thick bundles of wires, lots and lots of wires. So when current passes through wires, what happens to those wires? Say your answer to the video. You should have said that when current passes through wires, the wires heat up. So the cables will heat up. What type of energy is that? Say your answer to the video. You should have said thermal energy. So the cables are going to heat up, but there's going to be an increase in thermal energy. Now, we've also got the fact that these transmission cables are very, very, very long. They're really long because they need to get the electricity from the power station, which could be miles and miles away from the consumers who are going to use it. I bet that your electricity is not produced very close to your house or apartment. I'm sure that your electricity is created miles away and then is transferred to you through these transmission cables. So because these wires are really, really long, what is the rule? What is the relationship between the length of a wire and its resistance? Say your answer to the video now. The relationship between the length of wire and its resistance are directly proportional. So the resistance of a wire or cable is directly proportional. So it's directly proportional to the length of the wire. I'm going to use the letter L. What that means is if you've got a really, really, really long wire, it's going to have a really high resistance. And it's the resistance of the wires that cause the cables to heat up. We call this, the cables heating up, resistive heating, because it's due to the resistance of the wires. This is resistive heating because the wires are heating up because of the resistance. So the people who make these things make sure that the cables have as low a resistance as possible. So they make the wires really, really thick. So they make the bundles of cables really thick. That reduces the resistance. They choose a metal which has a low resistance to make these cables, but there's only so much they can do. The cables are still going to have resistance, so they're therefore going to heat up. Why is that a problem? Why is it a problem for the cables to heat up? Pause the video, have a think. Once you're ready, press play. So the reason why it's a problem for these cables to heat up is that if the cables heat up, energy is going to be transferred to the surroundings. Energy is going to be dissipated. Energy is going to be wasted. We don't want to waste this energy. We want this electricity to be transferred to the homes with as close to 100% efficiency as possible. So we're going to have to do something about this. We're going to have to try and reduce this amount of resistive heating. And the way we do that is by thinking about this formula here. So this is a formula which we've studied. Please say that equation in words. Say that equation in words. Say your answer to the video now. You should have said that power equals current squared times resistance. Let's just check you know the units. What are the units of power? Say your answer now. You should have said watts. What are the units of current? Say your answer to the video now. You should have said amps. And what are the units of resistance? Say your answer to the video now. You should have said ohms. Now, if you have a look at this formula, you can see there are two things which are going to contribute to the wasted power. So this is the wasted power in the cables. What does power mean? Say your answer to the video. Energy per second. So this is our wasted energy per second, and it's dependent on two things. You can see it depends on the current and the resistance. So the wasted power depends on the current and the resistance. So as I've already said, they try and design these cables to have as low a resistance as possible, but there's only so much they can do. So we want to reduce the current as much as possible. So our aim is we want to decrease the current, because if we decrease the current, that will reduce the wasted power. And if we can reduce the wasted power, does that increase or decrease efficiency? Say your answer to the video. You should have said that that increases efficiency. If we are reducing the wasted power, we are increasing the proportion of power which is transferred usefully. So we want to decrease the current to reduce the wasted power. I'm just going to show you an example of this. So using this formula, let's say we have a current of 1 amp and a resistance of the cables of 400 ohms. So that's a pretty high resistance, but let's just say, for argument's sake, that the resistance is 400 ohms. Please pause the video to work out the wasted power in these cables. Press play once you're done. So you should have found that the power is current squared times resistance. That would be 1 squared times 400, which is 400 watts. What does 400 watts mean in terms of energy? So I want you to give me an answer which talks about joules and maybe time. Say your answer to the video now. $400 watts means 400 joules per second. That's every single second, 400 joules of energy wasted from these cables. Now there's 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and these transmission cables are going to be working the whole time. That's going to be a massive amount of wasted energy. So we don't want that. We want to try and make this current as low as possible. So really the resistance would probably be lower as well, but we're looking at the current here because that's what we control with the step-up transformer. So the current, let's say we can get the current down to 0.1 amps. So we've divided the current by what? What have we divided the current by? You should have said we've divided it by 10. And we're going to keep the same resistance, so we're not going to change the cables at all. I'd like you to work out the power wasted in the cables now. Pause the video while you do that, press play once you're ready. So you should have found that the power is 0.1 squared times 400, which is actually 4 watts. What has the power divided by? Say your answer to the video now. The power has divided by 100. So by dividing our current by 10, we can reduce our wasted power by a factor of 100. We can divide our wasted power by 100. So it's really, really powerful to reduce the current. So to summarize what we've said that these transmission cables are very long and have resistance. There will therefore be resistive heating as current passes through the cables. If there is current passing through the cables, the wires are going to heat up. There's going to be energy wasted, transferred to the surroundings as thermal energy. Energy is going to be dissipated. That's going to reduce the efficiency of the electricity transfer. There's going to be wasted energy, wasted money. The wasted energy is the more important problem. But if we can reduce the current, we can reduce that wasted energy. So the way that we reduce that current is by something called a step-up transformer. So a step-up transformer. So the electricity from the power station goes straight into the step-up transformer. So here is our power station. So that's our power station. I'm drawing it as a box. Why not? And let's say the electricity in the power station is made at 25 kilovolts. And then that electricity from the power station goes into a step-up transformer. Step-up transformer. And from there it goes into the electricity pylons. And then it goes into this thing called a step-down transformer. And then to the consumer, so maybe your home. Now, what the step-up transformer does is it increases the potential difference. And by increasing the potential difference, it decreases the current. We'll talk about how that works. And by decreasing the current, as we've discussed, that reduces the thermal energy transfer, so that reduces the heat wasted, so it reduces the wasted heat energy, which increases efficiency. So that's just a little summary of what the step-up transformer does. But we need to focus on this increasing potential difference, decreasing the current. How does that work? So what the step-up transformer does, through a mechanism that we'll learn about another time, the step-up transformer increases the potential difference from the power station from whatever it was to a much, much higher value. So a standard value might be 400 kilovolts. So at the power station, the potential difference is 25 kilovolts. In the power cables, the potential difference is 400 kilovolts. So the step-up transformer has increased the potential difference from 25 to 400. Could you quickly work out what has 25 been multiplied by to make 400? Pause the video while you work that out, press play once you're ready. So you should have worked out that the voltage has been multiplied by 16. So when you do 400 divided by 25, you get 16. So what this step-up transformer has done is increased the voltage 16-fold. It's multiplied the voltage by 16. And you know what? That actually reduces the current to a 16th of its original value. It actually decreases the current. It divides the current by 16. So the step-up transformer multiplies this voltage, in this case by 16, and that divides the current by 16. And let's look at why that happens, how that happens. So the relevant formula here is P equals IV. Could you please say that equation in words? Say your answer to the video now. So in words, that equation is power equals current times potential difference. Let's check you know your units. What are the units of power? You should have said watts. What are the units of current? You should have said amps. And what are the units of potential difference? You should have said volts. So let's look at how this equation shows you that the current will reduce if we increase the voltage. So the electricity at the power station is going to be 2 megawatts of power. And that 2 megawatts of power is transferred to the cable. So that's going to be our power. What I'd like you to do is work out if the power is 2 megawatts and the voltage is 25 kilovolts, what is the current? Pause the video while you work that out. Press play once you're ready. So you should have worked out that if the power is 2 megawatts, that's 2 million watts, and the potential difference is 25 kilovolts, that's 25,000 volts, the current is 80 amps. So to do that, you should have done 2 million divided by 25,000. Now I'd like you to do the same thing, but this time the power is 2 megawatts and the voltage is 400 kilovolts. Pause the video to work out the current now. Press play once you're ready. You should have found that the current is now 5 amps by using this formula over here. So just by using that formula, you can see that when the voltage has multiplied by 16, what's happened to the current? Say your answer to the video now. The current has divided by 16. So what the step-up transformer does is it increases the potential difference, which decreases the current. That means we now have a lower current in the cables, which reduces the wasted heat energy. It reduces the resistive heating, which means we get less dissipation, less wasted energy. That increases the efficiency of the transfer. We also have the step-down transformer on the other side. The step-down transformer just decreases voltage back to safe levels. So to summarize, the electricity is made in the power station. The step-up transformer increases the voltage, which decreases the current, which increases the efficiency of the energy transfer because it reduces the resistive heating in the cables. The step-down transformer decreases the voltage back to safe levels. I recommend, if that all seemed quite a lot in a very short amount of time, rewind the video, watch it again, and then we're going to do a couple of examples. Here's our first example. Pause the video and have a go. Press play once you're ready. You should have now had a go at this question. So to start, it says how much energy will be wasted per second. What is the word for energy per second? Say your answer to the video now. Hopefully you've said that energy per second is power. So this question hasn't asked for power, but it actually has asked for power. It said how much energy will be wasted per second. What that means is what is the power wasted per second? So we need to find a formula which links power, current, and resistance. What is the equation which links power, current, and resistance? Say your answer to the video now. The equation which links power, current, and resistance is power equals current squared times resistance. So let's put in the numbers. The current here is 3.2. So we're doing 3.2 squared, and we're timesing that by the resistance. Now you're always allowed to use a calculator in physics. So 3.2 squared times 12 equals 122.88 watts. Now both numbers in the question were to how many significant figures? Say your answer to the video. Both numbers in the question were to 2 significant figures. So let's give our answer to 2 or 3 significant figures. Let's give our answer to 2 significant figures. What is this number to 2 significant figures? Hopefully you've said it's 120 watts. So there we go. That is the amount of energy wasted per second. Here you could also give your answer as 120 joules per second. They mean the same thing. 120 watts and 120 joules per second mean the same thing. Let's do another example now. Pause the video, have a go at this question. Press play once you're ready. So you should have known how to go at this question. We're being asked to calculate the current before and after. So what is the equation which links power, potential difference, and current? Say your answer to the video now. So the equation which links power, potential difference, and current is P equals IV. Now we need to remember to change our units to the standard unit. So we need to change the megawatts to watts, and we need to change the kilovolts to volts. So let's do that. So let's have a before and after, so we can work them out separately. So before, what is the power in standard units? Say your answer to the video now. You should have said 480 million watts, or 480 times 10 to the 6 watts. What is the voltage before the step-up transformer? Say your answer to the video now. You should have said 8,000 volts. So what we've done there is we've changed the megawatts to watts and we've changed the kilovolts to volts. Now let's do after. What is the power after? Say your answer to the video now. Well, the power is still 480 times 10 to the 6 watts. That doesn't change. The power that's been made in the power station is transferred to the homes through the national grid, so we still got that same power. But what is the voltage now? Please give it to me in standard units. Say your answer to the video now. You should have said 160,000 volts because we need to change the kilovolts into volts. So in each case, we can work out the current by just doing the power divided by the voltage. So I'm going to do that for both. So 480 times 10 to the 6 divided by 8,000. That gives 60,000 amps. Now that's just a silly number of amps. That's far too much. Let's now go to this one and do I equals P over V. So let's do 480 times 10 to the 6 divided by 160,000, and that now gives 3,000 amps. Now, the truth is these numbers are not very realistic. In reality, the current in the wires would be much lower than these numbers that we've worked out, but we're just practicing using the equations to understand the principles. So we're also asked to explain how this increases efficiency in the national grid. So if you've not yet done that, please pause the video to do that. Please write a written explanation of that and then press play once you're ready. So there's multiple steps to explain how this increases efficiency in the national grid. So you should say that decreasing current, so you need to mention that the current has decreased. So let's number this. So let's do 1. The current has decreased. The next thing you should say is that because the current has decreased, that reduces resistive heating. So that's the heating of the wires due to the resistance of the wires and the current passing through. So this reduces resistive heating. That reduces the energy loss to the surroundings. What's the word that begins with D, which we can use to say that? You should have said dissipation. So it reduces the dissipation. It reduces the energy loss to the surroundings. We should mention the type of energy there. So the thermal energy loss to the surroundings. So it reduces the thermal energy loss to the surroundings. And overall, that increases what? Say your answer to the video. So you should have said that that increases the efficiency of the energy transfer. So that is a calculation and a description and an explanation of how step-up transformers increase efficiency in the national grid. Please pause the video to do these questions. Press play once you've done them all. You should have now done all of these questions. If you've not done all of them, if you've not had a go at every single one, pause the video and do them. Press play once you're ready. So now you should have absolutely done all 13 of these questions. Please mark questions 1 to 8 using these solutions. Pause the video while you do that. Press play once you're ready. You should have now marked these 8 questions. If you struggled with anything, you can go back to earlier in the video to watch the explanations again. Please now mark the rest of your questions using these solutions. Pause the video while you do that. Press play once you're ready. You should have now marked all of these questions. If you have any further questions, you can write them in the chat below the video. Thank you for watching this video. I hope it was useful. Please like and subscribe to get more videos on GCSE physics.